А Сачков Александр так и не появился, да, у нас еще? Николай Васильевич, если вы меня слышите, можете позвонить. Вот,
Подключается.
Отлично. Так, я думаю, что мы можем начинать, потому что трансляция уже тоже началась. So, hello everyone, my name is Alina Boyka and I'm your moderator for this section. And today in first section we have 4 presentations, and all presentations should be in English, question also should be in English, and if you have some problems we can translate, we can help to translate or understand questions. During the presentation, all audience be muted. After the end of the presentation, you can unmute yourself and ask your question. And also you can write your question in chat in Zoom, or for our audience in YouTube, you can write comments and we will ask your questions. So each report should be not more than 15 minutes. It's 10 or 12 minutes for presentation and 3 or 5 minutes for questions. And if somebody not coming, we should wait 15 minutes and can discuss anything what you want, but in English. So I think that nobody have question. If nobody have question, we can start our section, and your chair for the section is Professor Dmitry Gromov, and maybe you want to tell something.
Yeah. So first, welcome everybody and good afternoon. So it's a pleasure to open this first regular session of our conference, which is devoted to the memory of Professor Vladimir Zubov. And as Alina already said, we have 4 speakers, we have 1 hour, so we don't have much time, and basically you should be quite brief in your presentation. And yeah, now I do not want to take much of your time, so I suggest that we go ahead with the first talk, and yeah, Alina is supposed to introduce the first speaker.
So first, our presentation is Alexander Kovshov, and your time is coming, so you can start. Alexander? Alexander? Just a second.
Oh, just a moment. Just a moment. I have a problem with internet. Do you hear me?
Yeah.
Can you see me?
Yeah.
Yes.
Well.
Okay. Yeah. We see your presentation.
Can you see my presentation?
Yes.
Well,
Alexander, your sound is not good. Oh. So Okay, we will wait.
Hopefully he will be back soon. So we still have some time. I believe we can postpone a little bit
Yeah.
the talk. So if it doesn't work, we can get some more, a couple of more minutes for that.
Alexander has come back.
Oh, excuse me, please. My internet's very bad now. I don't know why. It's a visit effect, I think. Just a moment. I try to show my presentation. Yes. Oh, excuse me, please. I will try.
Okay, you can start.
To continue. At a large hotel, taxi cabs arrive at a rate of lambda, and parties of riders arrive at rate of mu. Whenever taxi cabs are waiting, riders are served immediately upon arrival. Whenever riders are waiting, taxi cabs are loaded immediately upon arrival. A maximum of 3 cabs can wait at a time. Other cabs must go elsewhere. It's necessary to find steady state probabilities of this being I taxi cabs and J parties of riders waiting at the hotel. Also, it is interesting to calculate what is the expected number of cabs waiting and the expected number of parties waiting. And what is the expected waiting time for cabs and the expected waiting for parties. This was original problem, and we extended this conditions of the problem that, for example, riders it takes time for riders to load their luggage. And the loading time is distributed exponentially with the rate of eta. In this case, the state transition diagram became two-dimensional. Original problem is reduced to queuing system with one server. In Kendall notation, it writes MM1, and their state transition diagram is one-dimensioned. In our case, it's more complete. Well, we have two types of jobs of type A and jobs of type B. Each jobs are in their queue for QA and QB. Maximal number of jobs inside the queuing system N and M consequently. Server can serve two jobs simultaneously, and it can serve only one job. And in this pair of jobs, each job must be of different type. After servicing, all jobs go away from queuing system immediately. Also, if waiting room is full, the arriving job can't enter the system and go away without service. Well, this is state. Just a moment. What is the state? We will say that our queuing system in state ij if there are I jobs of type R in the system and J jobs of type B in the queuing system. And this is a state transition diagram. We can see transitions from one state to another. This diagram is similar to diagram for tandem QoS, but there is a significant difference. In that diagram, the zero row in the top of the diagram, and in our case, the zero row at the bottom. So we hope that we can use the result of tandem QoS, but unfortunately, this difference is essential, and results are essentially different. Well, now about the results. We considered two partial cases. First of them, oh, just a moment, I forgot to say about characteristics. Here, formulas for probabilities of denial of service. The probability that an arriving job will go away without service for type R and for type B. And lambda with title and mu with title is a number of jobs entering to the system per unit of time. Average number of jobs in the queuing system calculates by this formula. And also using Little's law, we can obtain average time that each job spent in the system. It's here. Well, first partial case. When when a system has no waiting room or only places for jobs in a server, and so this is only 4 states, and state transition diagram looks like here, and this is probability, state probability, equations for state probability. Yes, and knowing that where P is, where P are the probabilities of each state. Knowing that the sum of all probabilities must be equal to 1, we can obtain formulas for each state probability. Well, the second partial case, when with unit waiting room, there are 9 states, and this is a state transition diagram. Unfortunately, the formulas for probabilities we obtained, but they're very long, and I think it is not informatively to show it because it needs a few slides to show it. And also we can't find any regularity, any law to extend these results to a general case. General case for arbitrary M and N, we solved numerically. We created a computer program that can solve this system of equations using Gauss method. But using of this program is restricted because the size of system matrix grows rapidly when m and n large. For example, if m and n equal to 10, the system matrix has 10,000 elements. To solve this problem, we created another computer program that simulate such queuing system. This is the result for computer simulation. Our computer program can work with large m and n, and also it can work with a few number of servers. And we can compare to results for one server queuing system and with 4 server queuing system. This queuing system has equal throughput because queuing system with one server has fast server, and queuing system with 4 servers has slow servers, but there's throughputs are equal. And we can notice that in first case, the queuing systems with one fast server is more effective because percentage of lost job is less than in second case. Summary, I can say that a queuing system, such model with opposite queues, we name it opposite queues because they goes toward each other. And this model is essentially different from models with tandem queues and with parallel queues. In future, we hope to study more complete models, for example, when 3 or more type of jobs. Here is literature. Thank you. If you have questions, I will try to answer. Thanks.
Okay, let's thank the speaker first. That was very interesting. Unfortunately, we didn't have much time to go into detail. But still, we have like 1-2 minutes for some brief questions, if there are anybody who wants to ask.
We have one question in chat.
Okay, go ahead.
First question, what capabilities for the control in this model, or it just analysis of the model? What is it?
Sorry,
Can you control this model? Are there some opportunities to control it, or you just perform some structural analysis? Like, can you change the length of the queue, for instance, to make it longer or shorter? Like, can you arrange for more caps in the line?
Yes, the original conditions was only for restricted queue for caps and unrestricted for riders. In our model, we considered both restricted waiting rooms because it's impossible to obtain formulas for unrestricted in unrestricted cases. But in our model, we obtain formulas for state probabilities for 2 partial cases, and we can calculate numerically in general cases for arbitrarily m and n, but m and n must be finite.
Right. Okay, thank you. So unfortunately, we don't have more time for questions, even though I would ask some. But well, let's switch to the second speaker, right? And Alina will present
Okay, yeah.
the second one.
Thank you, Alexander. Thank you.
Thank you very much.
And our second speaker is also Alexander, but Alexander Sachkov.
Yes, hello.
Hello.
Hope that the audio is clear and the picture is not too terrible. I'll now switch to my presentation. Okay, there it is. Okay, just a second. Okay, can you see it clearly?
Yeah.
Okay, so should I begin now?
Yes.
Okay, so good day to everyone watching and to all of my colleagues present today. My name is Alexander Sachkov. I currently represent both the International Mathematical Institute of Leonhard Euler and the Faculty of Applied Mathematics and Control Processes of the St. Petersburg State University. And the topic of my talk today would be something very vaguely represented by choice modeling in insurance. So a couple of words, like initial remarks first. When talking about mathematical models, we must always take into consideration the fact that they are not representing the real-life object or system of objects perfectly. There are always some deviations, and the central task of mathematical modeling in general is to find the balance between the ability to actually use the model to get some results and the accuracy of the model. So how closely does it represent the real-life object? And the topics of discussion in my presentation would be axiomatic choice theory, just briefly, and we then will compare in a model example two approaches for solving actuarial problems. Which difficulties arise when dealing with choice usually? There are several, but three main ones are low mathematical rigor, in a sense that the methods used were intuitively easy to understand, but they were not proved. There were no concrete theories, mathematical theories to back them. Also, the choice is everywhere in our lives, so the range of problems is also accordingly wide. And since this range of problems is so wide, you sometimes have difficulties understanding where you should use which method to solve this particular problem. So what is the axiomatic approach and how is it different to a more traditional one? It is completely mathematically strict, so it builds from ground up from several naturally arising axioms, and everything else is derived from them. And also it provides clear calculational algorithms, since sometimes you have a very strict theory, but you can't really use it outside of, well, creating more of the same strict theory. This is not the case. And to advance in our discussion, we have to consider some things from actuarial sense and choice theory first. So we are just going to go through these definitions quickly, since they are more for for expositional purposes than for something strict. So usually you deal with a random variable x, which is an age at death of an individual. It's discrete with a period of 1 year, and f of x, it's a distribution function. Well, it depends on the problem which of these two you use. You will sometimes also use the complements of both x and f of x, called the survival function and time until death random variable. Also, for convenience, sometimes these two values are introduced. So the probability of individual x to die earlier than at x plus t years, or the opposite probability. The values for these variables can usually be gathered from live tables, but that's outside of our topic of discussion for today. This is just the sample problem, once again, to to set the framework for like what actuaries usually deal with. So we have some individuals who individuals, X years old at the moment. They want to buy a policy which would, if they survive for n years, yield them 1 unit of some currency. And they pay premium in return for this contract. And we have to calculate this payment to account for the interests of both parties here. Well, that was for actuarial mathematics. And now let's move on to the choice theory. We have three main things, three like very basic definitions, which everything depends on. And these are X, the set of feasible alternatives, which is of completely arbitrary nature, which is a pretty important factor in the future discussion. So these could be cars, mobile phones, I don't know, plane tickets, pretty much whatever you want to choose from. Then the vector criterion is the function of n values. So we take the feasible alternative and map it to the n-dimensional vector. So we simply rate this thing we want to choose on like n criteria, like weight, price, etc. And we also have the preference relation on X, which allows us to compare two alternatives. Important to note here that the preference relation is dependent on the person who makes the decision or the decision maker. This will be introduced at a later stage. So having those three definitions, we then introduce the multi-criteria choice problem. Given X, F, and the preference relation on X, we have to find the C of X, the set of selectable alternatives. So these are the things that we actually choose from a large pool of alternatives. So we have like millions of, thousands of mobile phones, and we present to the user or the decision maker in the end like 10. So then he can, his choice wouldn't be that difficult as previously. As I've stated, the elements of X are of arbitrary nature. So it's very important to understand that we can't exactly in mathematics work with cars in their like natural form. So we can't add up two cars or like divide one car by another. So we map to the cars the set of criteria using F. For each thing in our set X, we get F of X, which is the n-dimensional vector of values of criteria for that thing. And we also induce from the preference relation on X, the preference relation on Y, which is defined as is shown on the slide. And the multi-criteria problem can be, well, redefined as follows. So we only have Y and the preference relation on Y, and we return C of Y, from which we can easily get C of X. So I've stated that the axiomatic choice theory is based on axioms. They're there. So briefly, a couple of words about each of them. So the first one, if the Y1 is preferable to Y2, then we don't choose Y2. Well, that's pretty simple. Also, why the preference relation on Y is transitive, because otherwise we can have loops where we can never make a choice.
I'm sorry, Alexander, 2 minutes. Yeah.
Oh, 2 minutes. Okay, so the next one is the criteria should be compatible with each of the criteria components, and that Y is invariant with respect to positive linear transformation. So we also have a quantum. Basically, it's something that lets us we get from the decision maker, and it allows us to compare values based on his own preferences. And the quanta can be used in strict mathematical sense. As I've said, the clear computational algorithms. So we have the initial one, and the formula on the slide shows how we can transform it using the quant. So we have an example with 3 policies, and we have to choose from them, basically. So these are the 3 policies. P is premium, and L is the claim, which the insured gets. Well, it's pretty clear that the first one is the best. So the problem is we did not consider all of the criteria that can arise in these situations. So we'll try to remedy that right now. So we choose another criteria, just one for now, and it is the aggregate reputation rating for the insurer. So the more well-known and more reputable company is naturally going to be preferable for people. So we have modified the policies accordingly. So R is negative since the higher the position is, the better. So it is negative for our purposes here. And by asking the DEM, we got the quantum W1 and W2, modifying, recalculated the criteria and modified the policies accordingly. And now it is clear that the policy 2 is the best. And it's important to understand that it's the best for this particular decision maker and not someone else. And so it is, well, should be kind of clear that the previous approach left this out, this particular preference of the decision maker. So we compared these 2 approaches and saw how the application of axiomatic choice theory can change things even in the very simple case, because the example was extremely simple, and it was for the reason it was because well, I'll talk about this a bit later. So what can be done next? We can introduce more criteria, we can collect quanta better, and we can develop an application to automate the process. And here are the references. The first one is for actuarial science, and the second one is for the choice theory. That would be all. Thank you so much for your attention. And if there are any questions, I will be glad to try to answer them.
Okay, thank the speaker. It was very interesting. And are there any questions? Do we
Actually, I have one question.
You have.
Okay.
Okay.
Alexander, in insurance, we have two general types of insurance. It's non-life and life. Yeah, you talk about only life insurance. Did you try your models in non-life insurance? It's like motor insurance or something like this.
Yes, thank you for the question. It is actually something I wanted to talk about. The axiomatic choice theory has this very, well, let's say pleasant property of working with pretty much any field of science where mathematical models exist and any like anything where you can calculate. So naturally, both life and non-life insurance can be, well, the models can be, this approach can be used in both life and non-life insurance models. And I haven't tried it yet, but it is in my future plans, naturally, because the example was very simple so that everyone could understand it. I hope that everyone understood what was going on, even if it was very quick. But yeah, certainly I will be looking into both life and non-life insurance models in the future.
Okay, thank you. Thank you. And yeah, unfortunately, again, we don't have much time for next questions. So we just go ahead and continue with the third talk. So, Alina.
Thank you, Alexander. And our third present, it's Lizhnina Yelena, yeah? Hello. You can start.
Hello, everybody. Today I have the topic about supply chain model. Just a moment. It doesn't work.
Can you try Control A?
I'm trying. I'm trying, but that doesn't work. Today I present you the supply chain model with random demand. The ability, what is the problem? The ability to timely and efficiently satisfy customer requests is one of the important competitive advantages of any organization, and one of the most effective tools is construct the model and look how can we optimize this model and this process. Modeling is complicated because we have encountered combinations of external and internal uncertainties. And these uncertainties significantly affects the planning of the optimal allocation of resources. And in this presentation, we solve the problem of constructing and optimization model of supply chain close to real life. This is a map of our supply chain. We consider a company that has a manufacturer with here is manufacturer with a warehouse and selling points of products. Delivery can be carried out either directly or through intermediate transshipment points, which have their own warehouses with limited capacities. The storage capacities of the transshipment points are limited. Before use, what is going on? Before use, components are stored in the manufacturer's warehouse, and sometimes it's possible the situation if it's not possible to store all components at the manufacturer's warehouse. In this case, third-party warehouses are rented. The manufactured products are delivered to points of sale, and the delivery can be carried out directly or through transshipment points which have their own warehouses. And we model each link step by step. For example, this part, suppliers. Let we have a set of companies which produces components that are supplied to manufacturers. Supplier number I, its company produces certain type of components, and let Xi be number of components. We have a number of components planned to release by supplier, and we can calculate the time for production all necessary components. Next link is delivery of components. We have, for example, we have transshipment points, and we have we can deliver components either directly or through intermediate transshipment points. Every transshipment point has own warehouses with limited capacity, but we need to pay extra money to store the components in transshipment points. And here we have also the number of components, and we can calculate the minimum time for manufacture of components and delivery for delivery components. Next stage is production. We have components. Company manufactures K-name products, and we have K type of product, and for this product we need the certain quantity of certain components, and if we have the planned quantity of finished products, we can calculate the quantity of components for production of these products. And of course, in this stage, we can calculate the time which we need to spend on this stage. Storage of components before use. Components are stored in the manufacturer's warehouse. In a situation when it is not possible to store all components at the manufacturer's warehouse, we can rent a third-party warehouses. The cost for storing components in third-party warehouses is equal to this. Next stage is product delivery. We have points of sale, and we can deliver our products to the points of sale. We can do this directly, or we can do this through transshipment points. And what is interesting here, of course, we can calculate the time for this, and we have to pay for using the for storing our products in the transshipment points. And the price, the money what we should pay for storage of components, we can calculate by this way. transportation costs, we can calculate by two parts. First part is we have cost of delivery of components. This is C. And C1 and C2, the cost of transporting components from the supplier company when we use the transshipment points and storage in the intermediate point. And we have two formulas for our expenses. And second one, when we first formula when we have the direct transportation, and second one when we use the transshipment points. And finally, we can calculate the general expenses when we put the expenses on every stage. We can calculate the total expenses for all chain. And to complete our model, we can assume that the demand for product with type K at the point of consumption, we can calculate as a math expectation, and we we can calculate these formulas. And here, this formula, when we don't need to store extra production, and this formula, when we have to store the extra production, we use the storage on transshipment points. The final problem is to maximize maximize the profit function, to increase the company's profit. And for this, the main idea is minimize our expenses. And to find the optimal plan, how to control the supply chain model, it's necessary to find the optimal transportation plan and the optimal size and frequency of orders for components and manufacturers' products of each type in order to minimize the cost in the chain.
I'm sorry, 2 minutes.
And the main, the most interesting idea is that during the transportation, we can meet uncertainty like disruption of logistic chain. And usually, traditionally, this kind of problem usually modeling like Markov chain. And traditionally, we say about dry interval when our supplier is disrupted, and vent interval when our supplier is good, in good condition. And we model this situation as a Markov chain with parameters lambda and mu, which disruption rate, it's probability that disruption is coming, and the mu recovery rate, it's probability the length of period when supplier is in dry period. And using the Harrison formula for the optimal order size, we can use this formula, but taking into account the possible disruption of supplier, but we are interesting to not stop our process. So the good idea is to take the reserve components for manufacturing. So this is the optimal size of order size, just to take into the mind the possible disruption. And this is the order size if we use the transshipment points. And finally, we made the numerical analysis of parameters for sensitivity of model for parameters. And the first figure is the sensitivity of the model on the parameter for disruption, the orders or optimal order size. Second, the influence the recovery rate on the order size. And the last picture is the dependence of the optimal order size on the cost of storage. The model is a little bit heavy, and when we put everything together, but it's workable and was checked on real life situations. And I'm finished with any questions.
Thank you. Thank you for the talk. And if there are any questions, please ask. Okay, if there are no questions, I just ask a short one. So are you able to solve your problem just using some analytical formulas, or you had to perform some integer optimization to get the result? So did you actually solve this integer optimization problem?
Yes, yes. For real life situations, we checked this. We checked this model, and it works nice. It works good.
Did you use some special software?
No, just
branch and bounce, like some homemade.
Just yeah.
Okay, we can discuss this later. It's not important.
Yes.
Okay, so since we are a little bit behind the schedule, so I suggest that we stop at this point and let the last speaker start. Okay, so Alina, please invite our last speaker.
And our last speaker, it's you, Dmitry, yeah? Dmitry Gromov.
No, it's not me.
Oh.
It's gonna be
Елизавета.
Yeah.
Okay. Евменова Елизавета. Елизавeta.
Yes, I'm going to present.
Okay, okay.
Okay, so if you see my presentation, let me start.
Okay, yeah.
Okay. The theme of my presentation is structural analysis of directed side networks. And these networks have really many applications in sociology, recommended systems, and also voting systems. And there are many approaches exist to interpret the structure and evolution of such networks. And today I'm going to view this problem mainly from two theories points of view. they are structural balance theory and status theory. And both of these theories postulate a number of hypotheses and suggest us investigate a given graph for the compliance. And as for original structural balance theory, it was developed to be applied for undirected sign networks. And I should say that we use mainly a specific structure called a triangle. Triangle is 3 nodes, each of which is connected with each other, at least with one edge. And as for structural balance theory, there are 4 types of triangles in this theory, and those of these types which allow full cooperation complies with balance theory, and the others do not. As for status theory, it interprets relation as primacy, acceptance, or rejection, and is applicable for directed networks. And in this theory, if one accepts another as having a higher status, the edge from first to second will be positive, and if lower, then it will be negative. So here, consider a triangle shown on the slide to show the difference between these 2 theories on the example. And here we would like to mark this edge from C to A from 2 theories' points of view. And the structural balance theory predicts that the edge from C to A will be positive, while status theory predicts that it will be negative. And also we can say that if we change the orientation of the edge CA to AC, both of the 2 theories would predict positive weight. And what we've done, we tested these 2 theories on Wikipedia adminship election data. And to test these theories means to recognize whether a given graph exhibits a particular structure which expresses itself in the prevalence of triangles of a specific type, so-called characteristic triangles. And the idea of approach is to find frequencies of triangles. We name them empirical frequencies, and compare them with theoretical ones. And talking about these characteristic triangles, they have 2 properties. First, that a triangle should occur in the network sufficiently often, and also that its empirical probability is sufficiently larger than its theoretical probability. And here I should say that we can't say what exactly mean sufficiently often and sufficiently larger. And what we've done, we just selected a threshold, and maybe it would be really interesting to vary it later in our later research. What is more, while the process of counting triangles, we face up with the problem of isomorphism, and I'm going to tell a couple of words about this problem. The isomorphism relation is obviously an equivalence relation, and all equivalent graphs define an equivalent class. And briefly say, we use the notion of symmetry to solve this problem. And for a simple graph, like shown on the slide, for this graph, it is quite simple to determine the number of symmetries. We can determine it by mere observation, just with the rotation. And we can easily see that this graph has just 6 symmetries. However, for more complex networks, for more complex graphs, this can pose a serious computational challenge. So it is quite clear how to result empirical probabilities I was talking about. So let me go straight to the problem of finding theoretical probabilities. I should say that W sub I is the weight of ith edge. And first of all, we define the empirical probability P sub I given in the Formula 1. Also, we define the probability that there are no edges between there are no edges exist between two arbitrary vertices, and this formula shown in Formula 2. And the probability of a given triangle gamma with a stick is the product of probabilities corresponding to the individual weights of the edges. However, this probability has to be adjusted to take into account the arbitrary vertices numbering, and since we do not distinguish between two isomorphic graphs, the computed theoretical probability should be also multiplied with the number of elements in the corresponding isomorphism class, as it's shown in Formula 3. And after computing empirical and theoretical probabilities shown on the slide, we evaluate their ratio in Formula 4. And this ratio will be the indicator of characterism. And now we can step towards our experiments. We analyzed data obtained from the network that describes the results of Wikipedia adminship elections. And what we should know about this graph is that if one person can cast one of three types of votes. First is for positive, against negative, and neutral vote. And this information about the elections is represented as a graph. The vertices of the graph are the users. They can be both administrators and regular users. And the weighted edges correspond to the votes cast. And Leskovec, Huttenlocher, and Kleinberg extracted all this data. So what we can say about the graph mainly. Table 1 lists some basic numbers about the graph, and table 2 contains the density coefficients and the triangle density, which implies that the network is rather sparse. However, as for a relative degree, it indicates sufficiently large voting activity. In table 3 and 4, some characteristics are introduced to describe the amount to which an edge is likely to be accompanied by a reciprocal edge of the same or of a different type. And table 3 contains edge mutuality. It is the ratio of the number of edges with a specific weight accompanied by a reciprocal one to the total number of edges with the same weight. And if the edge binarity coefficient is sufficiently large, sufficiently high, then the vote of particular type is likely to be accompanied by a mutual vote. And it is not necessarily that it will be of the same type. And as for table 4, it presents reciprocity coefficient. And this coefficient measures the probability that given an edge with a specific weight, there will be a reciprocal edge with another specific weight. And the reciprocity coefficient is computed as conditional probability as written in the Formula 5. And here table 5 contains the data describing the triangle structure of the graph. I can say just some words about this table. We noticed that only 4% of all triangles have 5 and 6 edges, while the majority of triangles have either 3 edges or 4 edges. And we have already observed some patterns in the results, which will be published soon. And now I can show just the example of these results, example of these observations, some of them. Just one.
Елизавета, 2 minutes.
Okay. And here we can see triangles with their ratio, and our observation, one of our observations was the transitive triangles dominate the circular one. We can see what means circular and transitive structures on the top of the slide, and such a structure indicates that indicates the presence of hierarchy, more typical for status-like relations, more yes, and it's more likely to be typical for status-like relation rather than for balance theory. And all this, all other observations and these observations will be published will be published soon. And so what do we have for now? We presented an approach to determine characteristic subgraphs. We solved the problem of isomorphism and analyzed a specific directed weighted network, Wikipedia adminship elections. Thank you for your attention. If you have any questions, you can ask.
Thank you. Was interesting. Now, I hope there will be some questions. So we are slightly behind the schedule, but we still have some couple of minutes, so we can ask some short questions. Are there any? Okay, since there are no questions, I will ask one. So basically, signed networks are defined as networks with only plus and minus relations. And you here consider the network where there are 3 relations, plus, minus, and neutral. So what kind of extra dimension does it introduce to this problem? What do you get from that?
Yes, what we've done is that we interpreted these neutral weights as relations of equivalence or low positive relations, but it would be really interesting to vary this interpretation and show the effects on the result.
Okay, thank you. So,
Thank you.
are there some more questions? Okay, great. So if there are no questions, I'd like to thank all our speakers once again, all 4 speakers. And I hope that there will be more questions behind this room and beyond this room. So if you have questions, you can contact the speakers directly. And now, thank you. That's it. So we close our session for now. Thank you.
Thank you.
Thank you.
So now we have a break for 10 minutes. And so see you in 15.
Good afternoon, ladies and gentlemen. Do you hear me?
Yes, yes.
Okay, I'm glad to open our session of nonlinear mechanics and solid state physics. And you probably know that at the beginning of our faculty there was 3 departments: the Department of Theory of Control, the Department of Theoretical Mechanics, and our Department of Computational Methods and Solid Mechanics. So we are proud to
Yulia, we can hear you. Okay. Юлия, мы вас не слышим.
Юля,
I switch.
Вот.
okay.
Now we can hear you.
So I'm glad that here not only participants from our faculty and also from our friend faculty. And the first report exactly will be delivered by Galina. You will deliver.
I'm here.
Okay.
I'm here.
So please.
I'm ready.
Okay.
Galina, you have 12 minutes for presentation and 3 minutes for questions. And I tell you when you have 2 minutes. Okay?
It's okay.
You can start.
My report is about elastic plastic bending of vertical supports of drilling platforms. We consider the elastic plastic bending of vertical beams with as the effect and own weight under a constant moment or a concentrated load of the end of the beam. The constant moment simulates the pressure of a uniform ice field, and the concentrated load simulates the pressure of an iceberg or ice hammock. Vertical metal beams are widely used in the construction of hydraulic structures. The photos we show now. Offshore drilling rigs in Gulf of Mexico, offshore drilling rigs in Norwegian Sea, offshore drilling rigs in Sea of Okhotsk, east coast of Sakhalin Island. The offshore drilling platforms construction is on the shelf on the freezing sea is, is an urgent state task. Professor Shchinek, Karl Natanovich, and his colleagues from the Peter the Great Polytechnic University presented in the book the main factors affecting the magnitude of the ice load. The main factors are the strains of ice and the foam on hydraulic structures. These factors were taken as a basis in the ESO standard of the International Meteorological Organization. Recently, many scientists often computed models of the integration of ice fields with obstacles. Mr. Politko investigated the impact of ice fields on single bearing and multi-bearing hydraulic structures with a vertical supporting part. In this work, a mathematical numerical model of calculation based of the finite elements method of cutting and ice field through the supports over hydraulic structures is proposed. These studies were used to access the ice load from a flat drifting ice field on the hydraulic structures of the port of the floating nuclear thermal power plant Academic Lomonosov in the city of Pevek, Russia. In this slide, Mr. Politkov's numerical model of ice field impact on drilling rigs supports a program based on the ANSYS source package. Here is a laboratory experiment of the Krylov Research Center on the effects of an ice field. However, analytical solutions and theoretical understanding of the accumulated experimental material are not enough. Therefore, the authors of the proposed work attempt to analytically solve the problem of bending vertical supports of hydraulic structures, taking into account the influence of ice pressure or lateral hydrostatic pressure of supports. We are exploring the possibility of nonlinear deformation during bending. The ice load often causes destruction, over-tuning, and shear of structures. In this figure, coastal lighthouses, the lighthouses Tanio, Björnklaken, Kemi 1, accidents and damage to lighthouses under the influence of ice load. We give an example of an accident from the very recent past on March 6. According to the Hydrometeorological Center of St. Petersburg, gusts of the northwest wind in the eastern part of the Gulf of Finland, the pressure of the ice field up to 0.6 meter thick was such that the vertical piles gathered in a bundle. Ice piles formed around the supports to up to 2 meter high, and the supports themselves received irreversible plastic deformation. Here is it. Irreversible bending of the supports, destruction of the nautical stationary leading mark. Photos were taken in March 2013 and provided to the authors Kovalyov. Traditionally, ice physical and mechanical properties are studied based on experiments of uni-axial compression of samples. According to Vissou, the modulus of ice elasticity for calculating ice loads should be taken in the range of from 1 to 6 gigapascal, depending on the ice temperature. The Poisson ratio for ice is on average 0.33. A significant characteristic is the tensile strength of ice. It should be noted that the tensile and bending strength of ice are significantly different. Bending strength is from 5 to 10 times lower. Values of bending strength can be taken in the range sigma f equal 0.1 1 megapascal. The most dangerous in the impact of the moving ice formation. Significant may be bending of supports when loading a large ice field. We consider now mathematical models of bending of vertical supports. Figura on the left, bending by lateral force simulating the impact of a monolith ice field. Figura on the right, bending with a constant bending moment simulating the effect of broken ice. We study the elastic plastic bending that is observed in most modern structures still used to describe the V, where sigma S is the compressive stress yield and sigma T is the extension stress yield for uni steels. Inequality there more or equal 1 is satisfied. We use standard Bernoulli-Euler hypothesis for beam and the illusion theory of perfect plasticity. The transfer shear deformation is ignored. Proceed to study the bending of the vertical beam under the action of constant moment, excluding the weight of the beam and hydrostatic pressure, where the plastic areas, plastic zones are shaded. W is the deflection, Z1, Z2 is a constant, as a constant, P is a hydrostatic pressure, M is a constant moment. If we consider a bending with weight and with hydrostatic pressure, we use as parameter d tilde, where gamma 1 specific gravity of the beam's material, gamma specific gravity of the shear water. The external load's moment is MO. If moment is constant, then MO equal this formula, or MO is this formula. Internal bending moments has a form in each cross section of the beam, this formula here, eta is gamma 1 minus gamma. The neutral axis offset ZO is a function of Z1 and H. We introduce new notations, MT, M star, MK. Values of they are determined by the form these formulas.
Galina, 2 minutes.
Thank you.
Actually, 1 minute.
Enough. We have the equation. Yes. Enough. We have the equation of the bending of the beam. This formula. Then the load, the solution of this differential equation is this. It is Airy equation, and now we have equation for load pair, and we have solution this equation and boundary conditions. So if we have elastic plastic zone, equation have the form here and Z, and the solution of this equation is possible only numerically. It is the effective stress in cross section X equal null, P equal MT from equal here is effective stress in cross section X equal null. The values of the moments may be seen here. The values of deflection in elastic case may be seen here. Analysis of results allow us to conclude when design it is imperative to calculation the supports of hydraulic structures, taking into account the hydrostatic effect, which has a reinforcing effect when the structure is stretched. Not a good agreement between the results of the analytical solution and the numerical calculation. The result calculation, according to finite element methods, are indicated in brackets. In this work, we consider two cases of an elastic plastic bending vertical beam. The results may be used to compare the solution using FEM and experimental results. The authors are grateful to Kovalyov and the Arctic and Antarctic Research Institute for the photos provided. It is a reference. Thank you for attention.
Thank you for interesting report. Maybe are there any short question? Oh, if no, I have one question. You showed us some pictures where we can see that the concrete fill tube was used as a drilling support, but your calculations are for beams made of steel completely. Are there any drilling support from steel only, but not CFT? Бывают ли поддерживающие колонны только из стали, а не наполненные цементом трубы? Галина, вас не слышно. Галина, вас не слышно. Так.
Слышно? Теперь слышно.
Да.
Теперь слышно. Значит, безусловно, что те, которые были показаны в услуге, опоры, да, они сделаны из металлических труб, залитых бетоном. Вот эти самые опоры створных знаков в услуге, они не выдержали. Если бы их сделали из чисто металлических стержней, пусть даже такого не очень большого сечения, да, но стандартного, допустим, 20 на 20 сантиметров, если бы их сделали из таких стальных балок, там не очень глубоко, там глубина всего 15 метров, они бы выдержали. Вот. Дело все в том, что бетон у нас не работает на растяжение, и как только начинается изгиб, так все, они хрустят, и поэтому вот получилась такая авария, которую достаточно долго, ну сейчас все перестроили, конечно, но вот это был очень типичный пример, когда лед всего глубиной 60 сантиметров вызвал колоссальные торосы, а торосы вызвали вот такую вот неприятность.
Thank you
for your question.
Interesting report. We have little time.
Thank you,
so,
Mrs. Chairman.
Yeah, thank you for interesting report. Next speaker, Sidova Olga, is here.
Good afternoon, distinguished colleagues. Let me present our paper devoted to stress analysis in a spherical pressure vessel.
Olga, we can see your presentation. Okay, okay. Now we see.
Devoted to stress analysis in the spherical pressure vessel with multiple notches. A second. To begin with, I would like to say a few words about the relevance of the problem. Pressure vessels are used in a variety of applications in both industry and the private sector. Some examples of pressure vessels are diving cylinders, compression chambers, distillation towers, and many other vessels in mining operation, oil refineries and petrochemical plants, nuclear reactor vessels, submarine and spaceship habitats, pneumatic and hydraulic reservoirs. Pressure vessels also appear as storage vessels and receivers for liquefied gases such as ammonia, chlorine, butane, LPG, propane, and so on. Sphere is the ideal shape to hold internal pressure. This type of vessel is preferred for storage of high pressure fluids. Loading and severe operating conditions often cause various defects on the surface of structural elements. Corrosion, as the vessels often made of steel, may lead to general wear and initiate the appearance of local damaged areas. One appeared surface defects act as stress concentrators, causing high local stresses and resulting in acceleration of destruction of structural elements. To assess the strength and reliability of the structure, it is necessary to carefully analyze the stress concentration near defects. A few years ago, the Weldon Institute investigated a corrosion failure in a 13-inch crude oil pipeline that presented in the photo. It regrettably led to an explosion and fire and the death of several personnel. The pipeline was designed to ASME, and the investigation found that corrosion resulted from the breakdown of the external coating. Many authors investigated the effect of surface defects on strength, fatigue life, and buckling behavior of structures experimentally and numerically. A large number of studies concerning the stress distribution, analysis of structural elements weakened by surface defects consider rounded bars and plates under different loading conditions. Some research analyze pressure vessels with surface cracks or pits. However, the stress-strain state of shells of evolution with multiple surface defects remains one of the insufficiently studied areas. Finite element analysis is one of the powerful tools for such problem, often used to estimate stresses in the vicinity of defects and in the whole structures. In this paper, we consider a thin-walled sphere under internal pressure with defects on its outer surface. The defects are assumed to have the form of hemispherical notches of the same size. In this paper, we assume that defects are located on one of the equators of the sphere. Uniform and random arrangement of defects along the equator of the sphere is modeled. Different numbers of notches are considered. We consider hemispherical cavities with the depth equal to half of its radius. Calculations are made in the framework of the linear theory of elasticity. It is required to analyze stress distribution in the vicinity of the notches dependent on their number for two cases: defects evenly spaced and randomly arranged along the shell's equator. To perform a finite element analysis, we built an array of 3D models of geometries of thin-notched sphere. The inner and outer radii of the shell were set to R and R, respectively. The radius of all the notches is 6 and the depth is 3 micrometers. Various numbers of defects were considered from 16 to 216. For each value of n, 2 types of geometry were built. Notches are evenly spaced and randomly distributed on the equator of a sphere. Python scripts were created to automate the modeling of random defects pattern. A series of finite element simulations were carried out by ANSYS Workbench package. The sphere is subjected to internal pressure P. The boundary conditions include frictionless support on the surfaces of symmetry. Okay, let's move on to the results of the research. The red points on the presented graph are built for notches evenly distributed on the equator of a sphere, while the green, blue, and maroon points show results for the random pattern of notches location. It is seen from the graph that for the evenly distributed notches, the stress increases with the M growing up to 236, then the stress decreases with the further increase in N. This could be explained by the rare redistribution in the stresses due to the interaction between the stresses fields of neighboring notches. Note that given sizes of the shell and the defects for an n greater or equal to 216, neighboring notches overlap. For the case of the randomly distributed defects, an interaction between the stress fields near neighboring notches is observed regardless of n, resulting in the non-monotonous change of the maximum principal stress as n grows. Moreover, the interaction between the stress fields around neighboring notches for the random pattern provides stress concentrations that are greater than stresses in the shell with evenly distributed notches for the same number of defects. It should be noted that maximal stress values for evenly and randomly distributed notches are approximately the same. Namely, the difference between the maximum values is 8.6%. However, for evenly spaced defects, the maximum is observed for the relatively small range of varying the numbers of the notches. While for the random distribution, the maximum is observed for the larger range of the number of defects. The maximal principal stress in the vicinity of the notches for the maximum and minimal distances between the neighboring notches is presented in these pictures. The maximum and minimal are calculated at the maximum and minimal distances between the centers of two neighboring spheres, served as the basis of corresponding notches, respectively. It is seen from the figures that the results for the evenly and randomly distributed notches do not close to each other. The maximum stress in the sphere appears to be significantly influenced by other factors rather than the distance between the two neighboring notches. On the basis of the above, the following conclusions can be made precise. Firstly, for evenly distributed notches, the maximum stress occurred near defects first increases slightly, then rises sharply, and then drops slightly as the number of the defects increases. Secondly, the significant increase in the stress concentration was observed when the number of defects grow, such as the notches get closer to each other. However, when neighboring defects are close to overlap, the stress starts slightly decrease with the growing number of defects. As for the random pattern of defects, overlaps between neighboring notches took place for all the considered numbers of defects. Besides, the maximum principal stress changes non-monotonous with the growing of the number of notches. Also, it was investigated that the stress concentration you have a question?
No, we're short of time.
Okay. Also, it was investigated that the stress concentration calculation for the randomly arranged notches were greater than stress in the shell with evenly distributed notches for the same number of defects. Finally, the maximum stress values for evenly and randomly distributed notches are close to each other. However, for evenly spaced defects, the maximum is observed for the relatively small range of varying the numbers of defects, while for the random distribution, this maximum is observed for the larger range of number of defects. As you can see, it was my first experience in representing a paper in the conference, and I would like to close with quoting a math professor from Denis Villeneuve's film Scotched. Thank you for your attention, and if you have any questions, I would be glad to answer and discuss.
Thank you for your report. It was interesting. Congratulate you with your first report at international conference. Are there any short questions? If no, maybe I can ask. Abdullah, please. Switch your microphone, Abdullah, please. Yeah.
Thank you for your report. I would like to clarify about the random distribution of the notches. How exactly were they distributed? Was there any specific law of distribution, any standard procedure?
It was a normal distribution. I used IronPython scripts and the function that I had in the Python was used.
Thank you.
Thank you very much again. And now I invite next speaker, Anton Platov.
Good day. Yes. Cheers. You can see my presentation? Yes? Okay. Good day. Pardon, but I will read my report. The title of my report is Investigation of Finite Amplitude Surface Waves in a Basin with a Floating Elastic Plate. The investigation is devoted to the study of nonlinear fluctuations of an elastic plate and their influence on the wave disturbances characteristics of the liquid under the plate. Fluctuations are formed by a nonlinear and linear interaction of harmonics of progressive surface waves. We will consider a homogeneous, ideal, incompressible fluid which occupies an unbounded basin of finite depth. The fluid surface is covered with a thin longitudinally compressed elastic plate. The plate and fluid are unbounded in the horizontal directions, and under assumptions that the motion of fluid is potential and the plate vibrations occur without separation. Further, under the plate, we will understand the noise. The problem consists in solving Laplace equation with initial and boundary conditions: dynamic, kinematic, condition at the basin bottom, condition at the initial time. Problem 1.5 is presented in dimensionless variables. The relationship between dimensional and dimensionless variables is presented here. The introduced designations are presented here too. In the dynamic condition, the total derivative, this factor kappa, can be transformed as follows. And so as dynamic condition take the form you can see here. Here in the dynamic condition, the expression with coefficient kappa represents the interior of the plate vertical displacements, the first term in the square brackets, characterizing the nonlinearity of vertical plate acceleration. The problem 1.5 will be obtained by the method of multiple squares, and as a result we will find the following equations 8, 10, defining nonlinear approximations. We know that terms f20 and f30, which enter in the right-hand sides of dynamic conditions for the second and the third approximations, are caused by account of the nonlinearity of acceleration of the vertical plate displacements. The problem 8.10 is formulated in the general case of unsteady perturbations. Let us solve the problem in case of interaction of traveling periodic wave harmonics. We will set the first approximation of the plate through surface elevation in this form you can see here. Satisfying the condition at the bottom and taking into account the relationship of wave characteristics through boundary conditions, we obtained velocity potential V1 and dispersion relation. After completing all necessary steps, we will receive that the basin surface elevation zeta and the fluid movement velocity potential phi in dimensionless variables up to the third order quantities are determined from following expressions. All variables are known, but they are not represented here. Note that solution is valid outside small neighborhoods of the resonance values of the wave number K1, K2, K3, K4. The following slides will present an analysis of the results. Let's consider the amplitude phase characteristics of the disturbance formed by the nonlinear interaction of two harmonics in the case of absence of longitudinal compressive force. Here, the dependence of critical values of the wave number on the liquid depth and the plate thickness is graphically presented for the specified values. The calculation results show that a fixed value of the plate elastic modulus, the increase in the plate thickness leads to a decrease in wave number values. In this case, an increase in the depth, basin depth, leads to an increase in wave number values. When the depth exceeds 70 meters, wave number values remain practically constant. Here it's illustrated the dependence of critical values of the wave number on the basin depth and models of ice plate elasticity when plate thickness equals ½ meter. The magnitude of the vertical displacement of the plate depends not only on its thickness and the Young modulus of its material, but also on the amplitude A1 of the second harmonics, which was defined from the solving of the problem. You can see here the first approximation and A1. And the sign of A1 can be plus or minus. Here and other slides, the dashed line are obtained taking into account the nonlinearity of vertical displacement acceleration of the plate and solid lines not taken into account it. It follows from slide that the value of A1 amplitude increases with increasing plate thickness. The influence of the nonlinearity of vertical displacements of the plate is manifested in a decrease in the values of A1 with an increase in the wave number. For a fixed thickness of the plate and small values of wave numbers, the amplitude of plate vibrations practically does not depend on the thickness and elastic modulus of the plate. However, the values of the amplitude A1 obtained with and without accounting for the non-linearity of the plate vertical acceleration are different. Here it's shown the distribution of the fluctuation frequency from perturbation by wave number, wave amplitude greater than 0 occurs 1 and 3, and amplitude less than 0 occurs 2 and 4. Other parameters you can see on figure comment. It's seen that taking into account the acceleration nonlinearity at A1 amplitude greater than 0 leads to an increase in the fluctuation frequency. Also, growth frequency with increasing the elastic plate thickness. The change in the sign of second amplitude A1 from plus to minus decreases the value of the fluctuation frequency at a fixed wave number. Now let's consider the amplitude phase characteristic of the wave disturbance in the case of presence of longitudinal compressive force. On the slide is shown the distribution of A1 amplitude over the wave number in case of presence of longitudinal compressive force. We can see that function A1 has a local minimum whose value increases with the ice thickness. The compressive force decreases minimum and makes the difference in the value for the fixed wave number obtained with absent and occurrence of compression. This slide is illustrated the distribution of fluctuation frequency by wave number when compressive force present and when it's absent, and ice thickness is 1 meter. Here, in the distribution of the fluctuation frequency, the presence of a compressive force manifests itself in a decrease in the frequency value at a fixed wave number. It can also be seen that with an increase in the wave number, the influence of the nonlinearity of vertical ice acceleration increases. The change in the sign of second interaction harmonic amplitude leads to decrease in frequency value, but the direction of the compressive force influence remains. On the next two slides, this slide and this, the nonlinearity components of the fluctuation frequency in the first and second approximation are shown, but I will not dwell on them due to time limit. And on this slide, the distribution of phase velocity over the wave number of a from finite amplitude wave is shown. It can be seen that the presence of compressive force decreases the phase velocity both with and without taking into account the nonlinearity of vertical displacements. When amplitude second...
1 minute.
What?
1 minute.
1 minute? Okay, 2 minutes.
Okay, 2 minutes.
When the second amplitude less than 0, the phase velocity obtained with regard to the nonlinearity of vertical acceleration is lower than obtained without regard for it. The influence of the compression retains its trend to decrease. And in the following slides, you will see how the perturbation structure changes when the amplitude phase and ice characteristics change too. From the graphs of the profiles, it follows that in the case of A1 greater 0 and the compressive force is absent, the phase velocity of the perturbation increases when taken into account the acceleration nonlinearity of vertical ice displacement, figure A and figure A2. When compression is present, the fluctuation phase is like from the profile formed when compressive force is absent. The maximum and minimum displacements with respect to the undisturbed surface are observed in the form of crests and hollow respectively. When a second amplitude less than 0, the perturbation profile is qualitatively and quantitatively deformed, figure B. For example, double hand bending profiles can be seen in places of the crests observed. Besides the phase velocity for the profiles obtained with taking into account the nonlinearity of the plate, vertical acceleration is decreased. And this, in the conclusion, the main results that were presented here briefly formulated. Thank you for your attention.
Thank you very much for your interesting report. It's really impressive work. Thank you. Are there any questions? Does your theory can describe a phenomenon of sloshing, or maybe the phenomenon of resonance you described connected with sloshing?
Sloshing, what does it mean?
Sloshing по-русски.
Можно по-русски лучше.
Ну, это такое есть на русском явление. Видимо,
да.
Тогда, может быть...
По поводу резонансных точек, просто из решения, from solution of this problem with we have in dynamic condition term which characterizes bending stiffness of the plate, and from this we have singular values. If we don't have these values, you can see what here you can see.
Yeah,
the line of 5. This is not ice in this case, and the curve стремится к нулю. When we have ice with this term D and Q, we have resonance values.
Yeah.
May I ask you?
Yes. Yeah.
What a soft package we use by computing? What a soft package we use?
This is analytic equations which которые я решал, потом получил и решал на Delphi.
На Delphi, понятно.
Ну, запрограммировал, да.
Ну, было бы, конечно, очень интересно положить это все еще на конечноэлементный метод, да, тогда можно будет увидеть распределение и напряжение в этих пластинах, где они там текут, как они, как смягчаются колебания, да, при возникновении пластичности, как пластичность, как масло снижает вот эти вот пики напряжений, что очень важно. Спасибо большое, очень интересный доклад.
Спасибо.
Really great work, thank you very much. And now, next speaker, Mikhail Grekov. Michael, are you here? Or Tatiana?
I don't, yes, I am here, but yes, okay. Do you see my presentation?
Yes.
Okay, let me go. The work I would like to present you has been carried out with postgraduate Tatiana Sergeyeva at St. Petersburg State University. This work is focused on the Girton-Murdoch surface elasticity model and its simplifications that are widely used in studying surface stress effect in solids at the nanoscales. This model is based on the concept of surface energy in solids, which was first introduced by Gibbs in 70th years of the 18th century. The basic goal of our work is to compare the complete GM model with its simplified versions in the general case of a planar surface, and specifically in the case of surface dislocation interaction within the framework of plane strain conditions. The GM model consists of constitutive equations and the generalized Young-Laplace equilibrium equation. At first, we derive the last equation in terms of complex variables for the general case of a curvilinear surface in the plane strain problem. Then, we give the governing equation in the case of a planar surface and solution of the problem for the surface dislocation interaction of the dislocation array in the half plane, and some numerical results of the problem by different versions of the GM model. The complete constitutive equation of the linearized GM model 1 and the list of 4 simplified simplifications used in the literature are presented in the slide. In here, sigma S is surface stress tensor. ES strain deformation, strain surface tensor. Tau 0 residual surface stress or named surface tension. Lambda S and mu S models, surface models like similar Lamé models for the bulk material. Nabla S, U is surface vector, displacement vector, and Nabla S is 2D Nabla operator. Simplified GM models used in the literature is follows. The first one is corresponds to the using only the first terms on the right hand side of equation 1. The second simplified version is used when the surface tension is negligible, is equal 0. The third versions is used when lambda S and mu S equal 0. And this is some exotic example, but it allows to Mogilevsky to investigate influence of surface tension and compare it with a complete GM model. The fourth examples, the fourth simplified versions is when the normal gradient of surface displacement gradient equals 0, or whole surface gradients, surface displacement gradient equals 0. And it should be noted that we can present another simplified versions. The first, the 5, but it versions is very natural. But nobody did it. To solve the boundary value problems within the GM model, we use the general Young-Laplace law as is equation 2. And constitutive equation of bulk material, general Hooke law, and inseparability conditions of the surface and bulk material, that is continuous of displacement at the surface. The example of cylindrical surface for the plane strain conditions is presented in this slide. In the case of plane strain problem, the surface stress tensor can be written as equation 5. GM model component of stress tensor of surface stress tensor is equal equation 6. And using this equation and complex variables, we derive the boundary equation of the origin GM model in complex variables as follows in equation 7. Here, sigma n and sigma nt is traction at the surface. R is the radius, curvature radius. U complex displacement. Zeta complex 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 variable, no, complex quantity. Okay, alpha 0 is the angle between tangential direction t and x1 axis at the point z at gamma. If we have plane surface, and for the boundary problem for half plane with surface stress, the boundary condition in this case is written as follows: equation 8, and from this equation one can see that 3 simplification leads to the 0 of normal traction sigma to 2. But it's a simplification, but in the complete Gurdon-Murdoch model, this traction doesn't equal 0. Using complex variables and complex and method of Musilishvili complex functions and analytical functions, we derive the problem to the boundary to the integral equations in unknown complex displacement u. Function q can be dependent on the traction at the surface, on the external traction at the surface, load and at infinity, and internal sources of perturbation in the bulk material, such as edge dislocation.
2 minutes left.
What? Unit?
1 minute left.
1 minute left. Okay. So we solved this problem with area of dislocation in a half plane, and solve by means of series complex Fourier series, and here we can see some numerical results that for the stresses at the surface, for the displacement of the stresses at the surface within half period of the area of dislocation. The dotted curves correspond to the classical solution. The rigid curve is the solution which takes into account surface stress. If compared, I know that the time is over. If you compare two figures, left and right, and look at the curved red line, you can see that the difference between them is maximum discrepancy over the core of the dislocation. I'd like to finish. I want to finish, so, but excuse me that I don't have another sometimes. Okay. Conclusion. The closer dislocation to the surface, the greater effect of both surface elasticity and surface tension. If I can to read this conclusion, let me know. Let me. The first term of constitutive GM equation alone can be considered only in the case of curvilinear surface. And most different simplified versions of GM model yield the same boundary equation in the case of planar surface, and so lead to the same elastic fields, except for the exotic versions, ms equals 0. And the rest of simplified version of the GM model lead to the zero normal traction at the surface, while this traction by the complete GM model has the same order as the tangential one. Thank you for your attention.
Well, thank you for interesting presentation. Are there any questions? Do you have a comparison between complete Gerten-Murdoch theory results and with this theory without tensile tension?
Without surface tension. So when surface tension equals 0, this one figure, and complete this one. Only when distance from the dislocation area to the surface equal 0.1, we have maximum discrepancy in the point over the dislocation core.
On the right, is there theory results based on the Gerten-Murdoch theory, but not complete? Yeah.
Yes.
Or
yes. This simplified. This went down with surface tension equals 0 in incomplete GM model.
Yeah, and are there any comparison with the results without any surface effects?
Without any surface effects. Here, this figure is the third, and one can see that classic solution and the solution with model Gerten-Murdoch compare practically is the same, but only over the dislocation core we see the discrepancy.
Yes, very much. Are there any other questions? Interesting report. Thank you all for the presence at this section. And we'll see in 10 minutes at 4:30. Yes, Anna? Alina, yeah?
Yeah.
So 10 minutes break.
Thank you.
Yeah.
10 minutes.
Люди разошлись или нет?
Да, ну нет, они, значит, просто выключили микрофоны. Вот. Так что, ну что, я займусь теперь следующим, да?
Ну, через 10 минут.
Заседание, да, через 10 минут. Ну, в общем, как всегда, я не успеваю.
Да, на сайте же было написано 20 минут, а потом они решили в последний момент поменять, а люди-то уже доклады приготовили.
Ну да, ну вот в политехе, когда были доклады, я тоже там пытался, значит, уложиться, но и не всегда. А вот некоторые просто не укладывались и просто докладывали, и их никто не останавливал. Вот, хотя вот вопросы там все делались не после каждого доклада, а отвели специальное время в конце, когда сессия заканчивается. В конце там полчаса дается на то, чтобы побеседовать у каждого, то есть с каждым пообщаться, задавать вопросы и так далее. Тогда,
ну, в принципе, так и надо, да.
Михаил, а не могли бы вы прекратить трансляцию, пожалуйста?
А я не О, конечно, да. А я думаю, что же мне надо сделать?
Спасибо.
Спасибо.
Кто-то может еще
что сказать? Саша, ты прослушала весь мой доклад?
Да, я прослушала, но я тут просто еще в политехе, поэтому так, я все послушала, но комментировать я пока не могу.
Ну, комментировать тут нечего, потому что я бы по-русски успел бы рассказать все, а по-английски вот как-то, значит, все время не хватает, да и по-русски тоже не хватает времени, потому что доклад 15 минут или даже 12, это, конечно, так, тезисно только. Вот.
Такая ракурс на картинке необычный. Весна или еще. Или непонятно даже. Немножко снежка. И опять какие красивые картинки здесь с Питером.
Это интересно, конечно, да, вот так вроде бы я не видел, чтобы так выглядело на этот собор, улица. Вечером, да, так фонари горят в темноте. Здорово. Это же канал, это же Мойка. Да? Но так видно, что как будто ее вообще нет, а тут только улица.
Да. Так это, наверное, на дорогу и есть. Мойка-то слева вот виднеется.
Да, да. Мойка слева, но ее не видно, только видно ограда. Здорово. Yulia Grigorьевna, next presentation, yours the next presentation. Окей.
Сейчас я тоже буду задерживаться.
Надо было дать Елаева или Кабрицу.
Елаева выпустилась, ее уже нет.
Ее уже нет? Ну я просто уже как-то... Да, действительно. Действительно, да.
Поэтому придется самой. Раз в год, когда говоришь по-английски, язык просто не поворачивается.
Ну да.
Это еще и стихи все зубовские тут. Смотри.
Да. Интересно, кто это поснимал-то. Ну, наверное, съемки чьи-то профессиональные взяты,
Видимо, да, но удивили даже съемки.
Угу.
Хорошее качество съемок, неожиданно даже. Что
Ну да.
так, что-то можно еще новое увидеть. Питер.
Глеб где-то в горах находится, что ли?
Нет, это старая фотография в Сочи. Ну, вернее, да, в Сочи.
В Сочи, да? Понятно. А я думал, прямо сейчас здесь, где-то там далеко.
Сейчас все не так весело.
Понятно. Я-то все на одном и том же месте. Все никак отсюда не выберусь.
У нас 2 доклада были про лед, чем-то связанных со льдом. Да.
Ага.
И первый, и третий. Вот Глеб увлекся, поехал исследовать.
Просто была большая скидка.
Ага. Так, ну у нас, по-моему, время уже, да?
Еще, по идее, пара минут.
Еще пара? У меня часы, значит, врут. Часы врут, да, еще 1 минута.
Видно презентацию-то у меня?
Да, видно. А почему-то она маленькая.
Маленькая?
Нет, ну вот, я не знаю, а у тебя на весь экран, да?
Нет.
Не на весь. А, так ты полный экран можешь сделать.
А, надо, да, так плохо?
Это неплохо, конечно, можно и так. Если тебе удобнее, так можно и так, конечно. Но, вообще говоря, меня заставляли полный экран делать, то есть там...
Лучше
Как?
полный экран.
Лучше полный, да? Так,
Так.
окей.
Просто все, что мы говорим, записывается, поэтому кто-то нас еще потом будет смотреть.
Так, а куда в полный?
А вот пока слайдов...
В смысле, на это...
Это PowerPoint, да? Ага, вот полный экран. Yes. Okay. Okay. Let's continue. Let me continue our session, and the next presentation by Yulia Pronina, please.
But I'm not sure what do you see. I have some troubles in my. Sorry. I don't know.
When you open your presentation, you can see all participants in Zoom. You just see the presentation, it's okay.
It was...
Your presentation disappear.
Yeah.
We don't see it.
Something.
Demonstration.
Yeah, I know, but I can see only black screen. Now you see or not?
Okay.
Yes.
Yes. But the whole screen.
Yes.
Yes. Okay.
Right. Good afternoon, ladies and gentlemen. My today's report is devoted to minimization of metal costs for pipes exploited under conditions of mechanochemical corrosion. In the introduction, I'll explain what the term mechanochemical corrosion means. Then I'll describe some problems of optimal design and will shortly consider one of such problems. So let's start off. Corrosion can cause expensive and extremely dangerous damage of construction. More than 90% of largest accidents in petroleum engineering are due to corrosion. Among some international scientific societies, there's a movement to draw public attention to the problems of corrosion, and study of mechanochemical effect is one of the actual problems in this field. So what does the term mechanochemical corrosion mean? Originally, term mechanochemical corrosion was introduced by Gutmann with respect to general corrosion facilitated by mechanical stress. To be more precise, for anodic dissolution of deformed metals, Gutmann derived an exponential dependence of corrosion rate on mechanical stress. However, in engineering practice, they have to rely on empirical data. According to experimental results, the rate of corrosion is often a linear function of mechanical stress when stress increases beyond a given threshold. For some metal media systems, this threshold can be 0. For some, as an effective stress in these corrosion kinetic equations, we will use maximum principal stress because it provides the best correlation with experimental results. In any case, when the chemical reaction from front propagation is enhanced by stress, we have to solve initial boundary value problem with unknown evolving boundaries. Corrosion leads to stress. Corrosion leads to thinning of the tube wall, which leads to stress increase, and increase in stress in turn accelerate corrosive wear, and we have a closed loop. And the question is how we can evaluate corrosion rate and tube sizes at any time. Let's turn to the description of the problem. Consider a linearly elastic circular pipe under internal and external pressures. The rate of corrosion are linearly dependent on mechanical stress. The pipe capacity is given by the fixed internal radius at the initial time. And we have to find initial thickness of the pipe or its outer radius so that to ensure the prescribed service life, T with asterisk, and to minimize its initial weight. Yes, let me little clarify this problem. Due to corrosion, of course, tube wall become thinner and thinner, are getting thinner and thinner, and stress increase with time. And for a finite service life, prescribed service life, we need to find such an initial thickness so that the stress reaches the given ultimate limit exactly at the prescribed service life. When the coefficient of corrosion inhibition is non-zero, then stress tends to horizontal asymptote. And in this case, the problem is to find such an initial thickness so that these horizontal asymptotes coincide with maximum allowable stress. Coincide but not a little intersect, how it's shown here. But what if we cannot set such a large initial thickness that will satisfy these requirements? In this case, we need to replace pipes, and so that we should find such an initial thickness so that to minimize the mass of each pipe with replacement related to its service life, to the service life of each pipe. Let's turn to the solution of this problem. In a more simple case, when internal and external pressures are equal to each other, there's a homogeneous stress in the pipe irrespective of corrosion up to complete dissolution. In this case, of course, we cannot use maximum allowable stress criterion, and we have used only minimum residual thickness criterion. In common case, first we need to establish the relationship between stress and time, and then we have to analyze the behavior of objective function, which can be expressed in such form. This term numerator is proportional to the mass, and below the service life of the tube, which are found in the first stage of the solution. Here we can see the behavior of such objective function for the absence of any protective films in the pipes. And we can see, as expected, the objective function first decrease with the increase in the initial thickness of the pipe. And it was surprising that after a certain minimum, this function grows again. But we could explain this fact as follows. If we want to increase the thickness of the pipe egressed by 1 centimeter, then for small initial inner radius, for small radius of this layer, the mass of such layer is smaller than the mass of the layer of the such thickness of the same thickness, but with a greater radius. And this explains a little increase in this graph with the increase in the thickness. As I said, this is the objective function for the absence of any protective film. Here we can see the behavior of objective functions for the presence of protective film with a given lives of protective film. And for this case, the objective functions can have 2 points of minimum, which depend on initial thickness of the pipe, and they also corresponds to the given service life of each pipe with the same initial thickness. And as we can see, the first point of local minimum corresponds to a very short service life of each pipe, and thus require frequent replacement of pipes. So to assessment the cost of the pipeline, it's necessary to take into account another factors such as the cost of time, cost of replacement, cost of protective layer, and so on. But from the point of view of metal consumption, it may be optimal to take a pipe of a minimum possible thickness. That's everything I wanted to say. To sum up, we solved the problem of minimization of average material consumption per the unit of the service life of a pipe covered with a protective film, and with the possibility of pipe replacements. For an uncoated pipe, the objective function has only 1 point of minimum, and for coating, the objective functions can have 2 points of local minimums, and we have to choose the global one. Thank you all for listening.
Okay, thank you for your interesting presentation. Please, do you anybody has some questions, please? No? No? We don't have questions. Yes. So thank you very much. We can go to the next presentation.
Yes.
The next presentation is Sommerfeld effects in two mass clusters with 3 degrees of freedom by Mikheyev Serge. Is here.
Maybe Petr Morozov.
Oh, yeah, Petr Morozov here.
Ah, Petr Morozov. Okay.
Good afternoon, dear ladies and gentlemen. My name is Petr Morozov. I am a researcher at Mechanobartechnika. Together with my co-author, Professor of St. Petersburg State University, Sergei Evgenich Mikheyev, we are pleased to present you our work entitled Sommerfeld Effects in Two-Mass Crusher with 3 degrees of freedom. It contains mathematical modeling of the operation of a two-mass cone crusher and its behavior on the approaches to Sommerfeld thresholds. Two-mass crushers give good gain and balance. In Mekhanobr and Institute for Problems in Mechanical Engineering of the Russian Academy of Sciences, there are current physical models of a two-mass dynamic system, made in the form of a vibration cone crusher with 9 degrees of freedom, with two independent unbalanced vibrators driven by a synchronous engine. It proved to be very promising, and it became the initial point of our study. In the model offered, the motor is equipped with guide Pi sub 2, parallel to the guide Pi sub 1, and the striker is mounted on springs S sub 2, attached to the lower part of the body. In addition that a great number of mechanical constraints have eliminated some mechanical and physical crushing processes, it allowed to simplify the circuit and to create an accurate mathematical model suitable for high-quality numerical analysis. The blue point in the circle indicates the unbalanced gravity center, or enters the bunker, after which it spills out onto the surface of the striker and crashes as the striker approaches the motor. Then it powers out in the outlet made in motor, and then in the outlet made in base. The figure shows the dynamics corresponding to the first Sommerfeld threshold. The striker moves with some phase delay in relation to motor, and the unbalanced gravity center moves with phase advance in relation to motor. The idle crusher dynamics equations were published by the authors in Vibroengineering Procedure last year. Now the function psi is added to simulate the crushing process. Z is the mortar displacement, Z dash is the mortar velocity, Z sub s is the striker displacement, Z dash sub s is the striker velocity. Z of t is the function that describes acceleration. Phi is the rotational angle of the unbalanced mass center counted from its lowest point counterclockwise. Phi dot is the angular speed of unbalanced rotation. I is the unbalanced inertia moment. J is the unbalanced inertia moment relative to the rotational axis. R is the distance between the unbalanced mass center and the rotational axis. M sub u, M sub b, M sub s are the masses of the unbalance, the mortar, and the striker. Kappa sub 1, kappa sub 2 are the stiffness factors on the bonds of the mortar with the base and the striker with the mortar. Omega is the magnetic field rotational speed of the engine. Mu is the coefficient characterizing the nameplate torque of the asynchronous engine. The physical parameters involved in the System 1 were taken close to the parameters of the mentioned above physical model with 9 degrees of freedom. It is preferably to search for function psi among delta functions, as they correspond to an instant change in the function, the derivative of which stays in the left part. Transform the System 1 according to this remark. Let psi of t be equal to a delta of t minus t dash, where a is some number. Then, replacing psi in System 1 by 0, we replenish 1 with non-differential equations 2, where the argument t dash minus 0 means taking the left-sided limit with the argument tending to t dash. We introduce two random variables, a, which is the force of the impact of a piece of ore on the striker and the body, and t dash, which is the time of this impact. We assume that the act of crushing must leave a noticeable shear 1 minus sigma of rapprochement speed of mortar and striker just before this act. Thus, we obtain for A the top score presented on the slide. The more we leave, the less sigma and accordingly A. Setting A of t dash is equal to VB of t dash, where V is a random value distributed on the interval from 0 to 1, does not violate the construction logic. A series of numerical integrations of the system of stochastic differential equations 1 and 2 with different power frequency magnetic field in the state of asynchronous engine, omega equal to 100 radian per second, 105 radians per second, and till 210 radians per second were performed. During each experiment, this frequency was unchanged. The construct was started from 0 initial values of the variables at idle, and the working stroke was switched on after the first second. Further, the process was investigated only up to the 10th second, since practical stabilization of the stochastic process was observed after 3 seconds at each given omega. 2 Sommerfeld thresholds were detected. The first is about 126 radians per second, the second is about 188 radians per second. On the second, Sommerfeld effect was much brighter than on the first Sommerfeld threshold. On the time interval from 3 to 4 seconds, the maximum and minimum of the following quantities were calculated: unbalanced angular speed phi dot, full energy E accumulated in the crusher, unbalanced energy E sub U, the difference between E and E sub U, Z, and the difference between Z and Z sub S. In the table for the differences, the functions maximum and minimum were denoted by overline and underline respectively. The same time interval was used to calculate the integral characteristics of the engine efficiency usage, which is the ratio of real power takeoff to the maximum possible for the engine and given omega. When both Sommerfeld thresholds passed, these parameters changed tenfold. For sigma equal to 0.01, two Sommerfeld frontiers at frequencies 125 radians per second and 190 radians per second were detected. The efficiency of the use of engine power increases on the Sommerfeld thresholds, on the first, on the second. A good illustration of what happens at the Sommerfeld thresholds is the plot of clearance change depending on the rotational speed of the magnetic field in the stator. In crushing processes, it is at the Sommerfeld thresholds, as it turned out in our experiments, that the crusher works most efficiently. So, in the design of the crusher, the parameters corresponding to the operation at a Sommerfeld frontier, which can be calculated according to the above model, should be laid down. However, it is known that dynamical systems exhibit instability when approaching the Sommerfeld thresholds. Therefore, after the installation is made, the proximity of its operation to the frontier frequency can be provided by a controller that changes the rotational speed of the magnetic field according to information on the difference between it and the unbalanced rotational speed, or simply interrupts the power for a short time. The study used the following literature. Thank you for your attention.
Thank you very much. Very interesting your presentation. And my questions: what do you do? Anybody has questions, please?
Where does this thing can be used?
I shall answer. This problem is very important in mining. When a big pieces of ore go from the earth, it must be crushed to the smaller pieces. For example, a modern coal power station used dust. So, and just from the mines, we can get approximately 10 centimeters or maybe 20 centimeters and more pieces of ore, coal. So it must be lead to the dust, or it's a very modern power station, and maybe last century it must be made approximately centimeters and 5 centimeters sizes. And this idea of crushing is also used in many other industries, such as, for example, rubbish crushes for very small pieces, which can be used for different uses.
Thank you.
Thank you. Any more questions, please? No questions. So I'd like to thank you for Morozov for your presentation, and Sergei Mikheyev for your answer. And our session is closed, I think. Yes. Today, the first hour session is finished.
Yeah, thank you very much.
Thank you.
Thank you
for participation of all. Thank you all.
See you tomorrow.
See you tomorrow. Okay.
And don't
Yes.
forget our plenary papers.
Yes.
Thank you.
Thank you. So we can remove our